Good morning, friends.
Morning, Doug.
Let's see, I gotta drag a couple things in. One of them is that. Okay. So we are going to expand on what we learned yesterday, which is good because it means we're gonna, I don't know, I don't want to say reteach, but we're gonna practice what we did yesterday. But before we kind of launch into that, how's your brain? Anything from your homework yesterday that threw you for a loop? That you want to ask about?
Can you give us some hints about 16? I'm kind of swimming there.
Yeah, let me take a look. Let's see, those weird 16 and 4.2. Can you put into words what you found troubling about it, if anything?
So for the previous equations, when we want to find the general solution, it's C1e to the whatever plus C2e.
Mm-hmm.
But because we have two of the, oh no, not 16, I meant 18, excuse me. But because we have two of the same root,
Yep.
we have y equals C3e to the 3x. I'm not sure how to, I guess, proceed. Like, wouldn't that just be, do we just plug in our initial equations and then solve for C?
Yeah, that's the one where you have repeated roots. And actually, I think I'll show you this right now. Well, I can't remember if I already have this posted for you. I'm pretty sure I do. I need to look, I suppose. But this is really the note sheet for this section. And if I were to zoom in on it, this is what we did yesterday. Rules for solving second order linear differential equations. Homogeneous, we said yesterday, that's code for equal to 0. But later on, we're going to go into what if it's not equal to 0, but not today. So we said yesterday, distinct real roots. In other words, two different answers. We said in the auxiliary equation, in other words, if you found two different R values, you found R1 is like 3 and R2 is like 4. In other words, you solved that auxiliary equation and you got those two different answers, then that's your answer. But what did we say yesterday? If they are repeated real roots, in other words, it's not 3 and 4, it's 3 and 3. Well, then notice it's e to the 3t, but then it's C2t e to the 3t. In other words, they're both 3, except for one's got a t in front of it. So that's the sort of the notes as to what we did yesterday. So the question is, did you start that? Did you say, yeah, cool, one of the answers is C1e to the 3t? And we said that's true. Like, that actually is an answer. It's just not as complete as it could be. That actually would work for that. If you went back to that question 20 equation, question 18 equation, and said, hey, I'm supposed to take the second derivative, subtract 6 from the first derivative, and add 9 to the function itself, that really will equal 0 with just that answer alone. But there's actually a second chunk to this answer where it's still e to the 3t. Looks the same, except for, hey, there's an extra t in front of this. And remember, taking the derivative of that is much more of a pain because it's t times e to the 3t, so it's a product rule problem. So that's kind of a special case. Does that help?
Yes, thank you.
And now today, my friends, we are looking at complex roots. And so let's go build that. In other words, what if you get a negative under the radical sign? So that's really it. Like we're still going to get an equation just like we always got, an auxiliary equation to solve. But remember, those don't always produce real answers. Sometimes it produces imaginary answers. And so this is such an interesting section because you before today would have said, oh yeah, whatever. So it's an imaginary answer. And I could write it down, but it's like it's imaginary. It's a good name for those numbers. So it's imaginary. And so it's really not going to produce an answer anyway. And so fine, some math teacher wants me to write it down, but it's kind of a non-issue. It doesn't really matter. Well, turns out that is the best model. I mentioned this going out the door yesterday. It turns out that's the model for the spring, the one that's actually imaginary. What? I mean, it's imaginary. I've never seen that happen before. And so that's kind of what I want to show you today. So dive in. So 4.3, an auxiliary, I think is how you spell that. Auxiliary equation with complex roots. Roots is the sort of the least usual word for this, but just complex solutions. You get a negative under the square root sign. You should be able to speak the language of math. I'm always using the correct terminology with you, but I'm also using the street knowledge with you at the same time. Like, can you read that and say, that sounds really complicated, but this is all auxiliary equation really means, and complex roots just kind of code for answers that have negatives into the square root signs. Like, that's not that hard. So you don't know this now, but this is an example of how that would happen. So if I gave you the second order linear differential equation that looked like this. Uh-oh. Just went black on me. So I'd like you to solve that. I think you can't see it right now, so I'm just going to say it again out loud. Y double prime minus 4y prime plus 20y equals 0. Can you begin solving that? While we wait for my computer to wake up, which it now has. So this looks just like yesterday until you actually get the answer to it, and then you realize, oh, I don't get whole numbers. So now what's the procedure? What do I do now?
Is it 2 plus or minus 4i? I could be totally wrong because I did it in my head.
I think that is right. Nice work, David. I want to quickly, while you're finishing this up, what we ultimately are doing now is just jumping to this. Like, we're immediately looking at that and saying, hey, here's the auxiliary equation. But I only did that once yesterday. I want to quickly rebuild that. Remember, I'm going to erase all this. But remember, actually, I probably won't. Remember yesterday, we sort of made the educated guess that perhaps y, the answer to this equation, the function, would be some e equation. And we decided it'd be e. And let's see, am I going to switch? Does it have to be x? Like, at this point, do I even know? Notice this is interesting. Because of the way I wrote this, I do know that the dependent variable is y, but do I know what the independent variable is? I actually don't know that, do I? Like, it could be x, but because I wrote y double prime instead of dy dx or dy dt. And so at this point, we actually don't even know what the independent variable is. Isn't that interesting? Maybe I'll screw with this a little bit and make it something else this time. We said yesterday it wasn't just e to the t. We saw that didn't work, but we said, hey, if there was a constant in front of that, then it actually worked, right? And so let's just quickly do that. So we said, okay, well, in order to put it back in up here, we have to have y prime. And so we say, okay, if r is a constant, if r equals a constant, then we said, okay, well, the derivative of e to the junk times t would be e to the junk times t, but then times the derivative of the junk. And for that reason, y double prime would be r squared e to the rt. And then we just plugged it back in. We plugged it back in to see if it was equal 0. So we said, okay, y double prime was r squared e to the rt minus 4 times y prime, which would be minus 4 r e to the rt, and then plus 20 times the y term, the equation that we actually guessed, e to the rt. And we said, is that equal to 0? And so what we noticed is, well, it would be. Notice every one of these terms has an e to the rt in it. So I can factor that out, and it leaves r squared minus 4r plus 20.
Really is so cool.
Yeah, it's totally cool, isn't it? I mean, you need to be able to build this stuff. That's the key thing. Don't just, as I did up top, just kind of jump to the auxiliary equation. I mean, that's great. So be able to do that, but be able to build this for yourself really quick. Because yeah, that's exactly right. Like if you're not getting like a chill down your spine right now, if you're not seeing this is cool, like you're not getting it yet. So yeah, this could be equal to 0. Well, not here. That will never be equal to 0, but this could be, right? And so that's why we started there. So as a shortcut, as far as the test is concerned, you can just not have anything there in blue. Just like write the auxiliary equation down and solve it and get on with it. But you need to understand that this is based on, this is the answer that we've posited. We've said this is the guess. We know we're thinking this is the answer, and it will be the answer if you find the right r. And so if you use the quadratic formula, and I'm going to, did I say that right? I always get quadratic formula and Pythagorean theorem mixed up. Yeah, quadratic formula. So we say negative b, so that'd be plus 4 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 20, all divided by 2 times a. And that gives us 4 plus or minus, let's see, that'd be 16 minus 80, which is, ooh, not good, negative 64 over 2. And so, again, your first reaction to this should be, there's no r. Like, well, there is an r, but it's imaginary. But, you sort of could continue with this, and you know that I is equal to so to proceed in previous algebra classes, we just said, well, let's let I for imaginary be the square root of -1, since there's kind of no such thing. We'll just sort of pretend it is, and then we'll just give it a letter name so it doesn't like throw us off track. And so then we would say, okay, well, then this is 4 plus or minus the square root of 64i, but the square root of 64 is 8, right? So notice this doesn't get us out of the woods. Like, it's not like there isn't a square root of a negative there. It's still there. But then notice, hey, isn't that cool? 4 divides by 2, distributive law. 4 divides by 2, and 8 divides by 2. And so we just found our r. So yesterday we said, great. We plugged it in and we were sort of done. But today it's kind of like, well, what do you do with that? Well, part of the answer is, yeah, plug it back in, you're done. So wouldn't y be equal to e? And notice that's actually 2 different answers. It'd be e to the r. And I'm going to use t this time instead of x. Doesn't really make any difference. So there's my r. But then we also said the other answer to this would be if it was a negative sign, right? We said y could also be equal to e to the 2 minus 4i, and that's all multiplied by t. Isn't that what we said yesterday? Is it any different? No, so 2 answers. But then we went on to say that, amazingly, you could even add a constant to each one of those. So I could put a constant in front of this one. And I'm going to write this a little different now. I'm going to distribute the t into both of those. I'll show you why in a second. So I just distributed the t. And the same thing would be true for the other one, e to the 2t minus 4it. And so we said those could have constants in front of them, and they don't even have to be the same constants. We call them C1 and C2. And then we even said, since they're linear, we could actually add them together and just write one answer instead of two separate answers. I mean, isn't that kind of cool? Isn't it amazing? So that's kind of neat. We wrote one answer to this, but remember, all you have to do is make C2 equal to 0. And then, you know, bam, there's the other answer. I mean, so it's not like you don't have each individual answer, right? So it's no different. Isn't this what we did yesterday? But again, you should sort of feel like, yeah, but there's no such thing as I. So, I mean, that's real great, good for you, but there's no such thing as I. There's not really a number that is, at least that we understand, we can touch and feel and taste in this time space continuum. And so good for you to write that down, but that's not really very helpful. Now here's where it gets really interesting. So we're actually not going to quit just yet. Now, you remember the rules of exponents. If you have an exponent with two things added together, couldn't you also write it like this? You could say C1 e to the 2t, and then what do you do with e to the 4it? They could both be written as raised to the e power, couldn't they? As long as I put what between them? Algebra students.
As long as you're multiplying them.
Multiply. I saw Hannah was lip smooth. I think she was on mute. Is that right, Hannah?
Yes.
We'll assume Hannah was answering the right answer instead of saying, I have no idea. So that would also be true. I could write it that way if I wanted to, right? And of course, that doesn't really accomplish anything, but I'm just writing it that way. So, you know, or I could, you know, kind of say it this way. Either of those things would be true. Now, does it make sense if I gave you initial conditions here, you wouldn't be able to do anything with them? Because I doesn't exist. As soon as you still like, get your graphing calculator out and graph this, or, you know, get Desmos out, it's not going to like this, right? Because remember, I is a number that kind of doesn't exist. So if you try to graph this, it's just going to say error. Now in Desmos, is it going to recognize I as being this? Like it recognizes E as 2.718, not just some random letter, right? Does it recognize I as the square root of -1? And so is it just going to say, dude, I can't graph that? Or is it going to just think, oh, it's a letter? You know, so I actually don't know. I think I would, but
If we did plug in 0 though, that would be 0i. Wouldn't that just be 0? That allows us to solve it technically.
what do you mean if you put 0 in?
If our t was equal to 0 for our initial condition, then 0 would be
Yeah,
multiplied by
that's a good
I.
point, right?
That
Yeah.
makes sense, doesn't it?
If our initial condition was at times 0, would that get rid of it? I think it might. Yeah. That's
It
actually
would
a
make
good
it
point.
so our constant isn't complex, but the complex number would still be in our particular solution because it's still our constants just wouldn't be complex valued.
Yeah, but the actual, yeah, that's true. It'd still actually be I there in your solution. But
Yeah, well said. But even if that was true, like we still don't have a graph. Does that make sense? Like you can't graph this. I mean, good for you. If you came back with C1 equals 9, like is it going to graph now? No, because there's an I in it. And so again, you should sort of feel like you just reached a dead end. Like, you know, turn the car around, head back 2 miles because you shouldn't have taken that turn because you're at a dead end right now. And so here's where it gets ridiculously amazing. Let's stall for a second here and take a look at something that you Math 253 people. If you didn't take Math 253 to get here, this is the only time when you're not going to have as deep of an understanding. but you may remember there were, you don't again, you don't have to know this, but let's stare at this right now. There is an expansion for e. In other words, e to the number, if you wanted e to the second power, let's just familiarize ourselves with this for a second. If I said, let's go in a different color. If I said I'd like to know what, e to the second power is, this formula right here, I'm sort of skipping the cool symbolism behind that. And that symbolism should make sense, but you probably still have a little bit of a, knee-jerk freak out reaction when you look at that. But this is really saying what's e squared? Well, notice I just picked x to be 2. So everywhere over here I see a 2 or an x, I'm just going to put a 2. So in other words, this is actually equal to 1 plus 2 plus 2 squared, which is 4 over 2. What's that symbol mean? Math 253 people?
Factorial.
Factorial. It doesn't mean 2. It means 2 times 1. And then 3 means 3 times 2 times 1. 2 cubed is 8. And of course, can you see the pattern? I said dot, dot, dot. Can you see what's happening next? Notice the next one would be 2 to the 4th over 4 factorial. 4 times 3 times 2 times 1 is 24. And notice how long does that go, Math 253 people? What's that mean right over there?
Infinite.
Forever.
All the way to my
Forever. Who knows where that movie's from? Forever. Sandlot, isn't it Sandlot? Anybody know? It's an old movie. Good movie.
For some reason, I was getting Monsters Inc. vibes. I don't know if that's where it was.
Somebody put it in the chat. Somebody don't pay attention for the next 5 minutes. Now, if you bust your calculator out, you can test this out. Unfortunately, the dot, dot, dot means you have to go forever, but this is not approximately equal to, my friends. It is perfectly equal to. Well, if you don't stop, if you never stop. But even with these 5 terms in it, if you get your calculator out and say e squared, and then you type 1 plus 2 plus 4 over 2 plus 8 over 6 plus 16 over 24, you'll already see it's getting at least reasonably close. Well, maybe not. 16 over 24 is still a pretty big number, isn't it? So maybe I'd have to have a few more terms than that. But that's a truth. That's a truth in the universe that you missed if you didn't take Math 253. And by the way, somehow I graduated from college with a math degree and I never had to take this class, which is just utterly ridiculous. This is really beautiful, but for some reason in my teacher training, like, oh, you don't need that. So, okay. So basically what we're seeing then is this e to the 4it right there. We could actually do something with that. So let's think about what this e to the 4it. Based on that expansion, that Maclaurin series expansion that we just saw, we said it was first 1 and then plus x. Well, remember this entire thing is our exponent, right? So it's plus 4it. And then it was plus x squared. So that'd be 16i squared t squared, wouldn't it? Oh, I feel like I'm doing something wrong. Actually, I'm going to write that differently. It's 4it. I'll just write it as being squared over 2 factorial. And then it was plus 4it cubed over 3 factorial plus 4it to the 4th over 4 factorial plus 4it to the 5th over 5 factorial. And it seemeth as though I am out of room. Isn't that what that said? Let's go back and look at it real quick.
Yeah, that looks right.
That's what it said, right? And by the way, notice you might think those first two are totally different, but is that x to the 0 over 0 factorial? Is this x to the 1st over 1 factorial? The answer is yeah. X to the 0 is 1, and 0 factorial, we won't go into this now, is also 1. X to the first is X, but then 1 factorial is 1. So that pattern actually, it's not like those first two are different. They're following the same pattern. Now, you should be thinking, this is not helpful.
Let's get.
We were at a dead end and now you're driving through the trees. Like, we're gonna die. Like, this is going nowhere. Are you thinking that?
Yeah, Doug,
Yes.
you're wasting our time. Why are you teaching us this?
Yes, you're wasting, exactly. That's what you should be thinking. But here's where it starts to get ridiculously interesting. And just when I thought you'd done every stupid thing, you totally redeem yourself. What movie is that from? None of you know? Dumb and Dumber. Come on.
Oh, I don't even feel ashamed about that one.
He sells their car and buys a scooter. Now they're all riding on a scooter.
Maybe I have to watch it, but I passed that so much even when VHS was a thing.
What's VHS?
No, that's not real. Stop it, David.
Now, let's think about something here. If I is the square root of -1, my friends, then what is I squared equal to?
-1.
I squared would be the square root of -1 times the square root of -1, which is actually -1. So although I doesn't exist, I squared does. Isn't that weird? And let's think about I cubed. I cubed would be, well, isn't it I times I squared? In other words, -1 times the square root of -1. So it'd actually just be negative the square root of -1 or negative I. Isn't that true? Again, you can always interrupt and say, hold on, wait a second, let me think about that. Again, these are sort of things you should know. What would I to the 4th be?
Oh, that's a -1?
Close. I to the 4th would be I squared times I squared.
+1.
It's actually back to +1. Because I to the 4th would be I squared times I squared, but I squared is -1. So it's -1 times -1. So notice when you get I to the 4th, you actually just get 1. So notice the even ones actually exist. The odd ones kind of still don't, but the even ones do. And do you see that there's a pattern that sort of starts right here in the sense that what would happen if I went to I to the 5th? Wouldn't that be I to the 4th times I? But every time you have an I to the 4th, it's just a 1. So you're kind of back to the top again. In other words, I is the same as I to the 5th because you can take an I to the 4th out of it. And I to the 4th is always 1. So if that's true, then I'm going to slightly modify what we have because notice in that third term, it's 4I t, but that's squared. Well, notice I squared is just -1. So would you agree that I could actually pull that out and make it negative, but then all the rest of the stuff still sits there? All I did was square I left the other stuff alone, but I just squared I, and I squared turns into -1. What does I cubed turn into? Well, it's just -I. So it's negative, and then there's still a 4t cubed. And there's an I there, not I cubed anymore because I cubed is -I. So I put the negative out there. Are you okay? We doing all right? Seeing that? And then I to the 4th is actually +1. So that means I can actually take the take the I, in a sense, kind of completely out of that statement. And then we said I to the fifth is just I. So I don't need an I to the fifth, I just need an I. Again, you should be thinking you're taking us into the forest to murder us. This is going nowhere. But now I would like you to stare at, well, look at all the I terms. Like this has an I in it, this has an I in it, this has an I in it. Notice those just have I values in them, right? So if I was just to look at that, does it make sense I could actually kind of factor the I out, and that would leave 4t for this term. And if I took the I out of this one, it would be minus 4t cubed over 3 factorial. And if I took the I out of this one, it would be 4t to the 5th over 5 factorial, and so on and so forth. You agree with that? I'm going to put that first 4t in parentheses. And then let's stare at the, well, the non-I terms. There's these non-I terms. And so those are 1 plus, and I guess it's minus 4t squared over 2 factorial. And then it's plus 4t to the 4th over 4 factorial, and so on and so forth. Notice, by the way, you can actually tell the pattern here. Like, can you tell what the next terms of these sequences would be, even though I didn't write them down? Notice the alternation, plus, then minus, then plus. And so the next one would be minus, and it went 4t squared, 4t to the 4th. So wouldn't this next one be 4t to the 6th? And it's always divided by the same exact exponent, but factorial. Wouldn't that be the next term down there? And with respect to the one above it, couldn't you see the next term there too? Like even without kind of writing it down? Let's see, it was 4t to the 1st, 4t to the 3rd, 4t to the 5th. I see the pattern, 4t to the 7th, and then divided by 7 factorial. What did I do wrong though?
Needs to be minus.
Good, it needs to be minus, because look at the pattern. It starts out plus and then it goes minus and then plus, and then, oh, that'd be a minus, wouldn't it? Again, what good is this? Good for you. Back to Math 253. What do you notice if I disappear the ugly part of sine and cosine for now? We don't need tangent. What do you notice right here? Does that look vaguely like what we saw written on the other page? This says sine of x, and then over here it's x, and then minus x cubed over 3 factorial, and then plus x to the 5th over 5 factorial. Isn't that kind of what we just saw on the other page? And then look at cosine. Cosine of x, and then I see I covered up a little too much of that. Covered up the one. Cosine of x, and then it started at 1, and then it was minus x squared over 2 factorial plus x to the 4th over 4 factorial. Dude. So let's see if I can do this a little more professionally. So these are complicated enough that we kind of need to be able to see them on the other page. Despite watching Dumb and Dumber and technologically advanced enough to survive this, I hope. I didn't watch all of it though. That's why I can still do this. If I'd have watched it all, I wouldn't be able to do this.
Did you actually not finish it?
I did not.
So what you're saying is it's not worth watching.
I'd say it's worth watching if you thought Napoleon Dynamite was funny, which I also didn't watch completely.
Yeah, I don't remember my opinion. It's been so long.
Getting mixed signals from you, Doug.
You blocked it out. You've all lost respect for me, haven't you?
I mean, I'll watch anything once, but if I'm gonna recommend it to others, it better be good.
True. So what are you seeing up there, my friends? What are you seeing?
Seeing sine and cosine.
It's exactly the same. Do you see that?
But we still have the I in our sign.
Yes, but that doesn't mean I's gone away, right? So I'm still tricking you, right? At this point, good for you. You wrote it differently. For those of you that didn't take 253 like this, you're going to be able to use a note sheet for this. It's not like you have to build this or, deeply understand this and so forth. So, we'll get there. And also, like, you're going to need to go back and rewatch this lecture and relook at my notes if you want to own this. If you want to own this, you don't have to choose to own it. But let's just stare at this for a second. So cosine of x starts with a 1. Hey, that's sort of with a 1. And then it's a minus. Hey, there's a minus. And then it was junk squared. Hey, there's some junk squared over 2 factorial. And then it was plus. Hey, there's a plus. And then it was junk to the 4th. Hey, there's some junk to the 4th over 4. It's exactly the same. You agree with that? Let's do the same thing with sine. Okay, let's see. It started out with an x to the 1st power. Hey, there's some junk to the 1st power. And then it went minus. Hey, that's a minus. And then it was junk to the 3rd. Hey, 4t to the 3rd over 3 factorial. And then it was plus. And then 4t to the 5th. Hey, there's an x to the 5th. Like, they really are the same. And so here's where we are. After this amazing discovery, which was both e and sine, we're now saying that y is no longer equal to this crazy long infinite series. What are we saying? Aren't we saying that it's equal to cosine of, well, not x, but what?
4t.
Yeah, our x is 4t. And then plus sine also of 4t, isn't it? Except for
No,
what
not
did I leave
either.
out? What did I leave out that's really important?
I.
Is that right? Did I leave anything else out? Is that where we are?
Looks right.
Looks like it.
And so
pretty
again, I mean, that's some crazy hand waving there, but again, there's still an I, so let's not get too excited.
That's pretty exciting.
It's beautiful, that's for sure. Now, just to kind of forecast something, notice in our note sheet that I'm building, if you will. Get rid of all my notes. Notice what I said here about complex roots. Complex roots where you have alpha plus theta I. For us a second ago, wasn't that like 2 plus or minus 4i? And so the alpha was 2 and the theta was 4. That's what happened for us, right? Then notice over here, y equals what? Y equals what? Did I say e to the 2t times e to the 4it? Is that what I said on the other side? No, I rewrote it with exactly what we just discovered. Except for, what do you notice is missing?
Do they know they don't have an I?
Yeah, notice there's like no I over there, right? like it got erased or something. And that of course feels like, what? You can't do that. What are you talking about?
Yeah, in the book, they're like, well, if you want to know, take complex analysis.
No, that's not true. If you want to know, I'm going to show you because you can't not know that. Let's see. Now something else is occurring to me. It's like, where did the, like, didn't that answer have the E in there too? Like, wasn't there an E to the 2t in front of those? So it's like, that's gone. Like, where did that go? Actually, I got to kind of look back and think about that. Where did that go away? Oh, that's right, because we just ignored it. In other words, didn't we, actually did not remember, but didn't we attack this right there and just kind of leave that alone for a little bit? Like I just left it off, didn't I? So we got all done, and what we ended up doing is replacing e to the 4it with something, but isn't it still multiplied by ce to the 2t? That makes sense? Like I just kind of left that off, forgot about it, right? So that is there, isn't it? Like it's, so it's not so much that y equals this. I should go back. I should say, because actually I thought it was when I was doing this. It's actually more like e to the 4it is actually equal to that, right? That's what we really discovered. So I got a little too excited. So if I go back here, is this what I want? No, I actually want this. If I go back here and re-grab our sort of previous answer, drag it down here, get rid of some of that junk. So then could we not say, my friends, that y then is equal to c1e to the 2t, except for it is multiplied not by e to the 4it, but by cosine of 4t plus I times the sine of 4t, right? And that's effectively just, well, this answer, isn't it? Now, what about this one though? Like we never attacked the kind of the negative e to the negative 4it. Like
Can we just flip the signs on cosine and sine?
that's kind of what it feels like to me. Do you agree with that? In other words,
Cosine of negative something is just cosine.
yeah, and that's kind of interesting too. And so let's see if I went back and I think, you know, what did I do with that 4i? If that had been a negative 4i, then wouldn't this actually, you know, have a negative? I'm just thinking out loud here with you. Wouldn't that be like a negative? But then what would happen here if this was a negative?
It would just get squared away.
It'd get squared away. That's exactly right. We'd square it. And so this would actually stay positive. That's kind of interesting, isn't it?
I wonder if the easiest way would just be to keep the negative in the 4i in parentheses and then just deal with it once we have done everything.
Yeah. Could I just keep it in there? In other words,
Keep it as part of the x term.
yeah, just like keep it in there for now. In other words, let's try this really quick. Let's just see what happens if I take this. Yeah, let's get rid of some of the mess of it. Let's choose the color black and let's say, okay, then, you know, what happens down here? Well, if that had been negative, to Ben's point, doesn't this become negative? And there'd be a negative in here and a negative in here and a negative in here and a negative in here, right? So what is that going to do? So I guess the 1 would be left alone, and this would become 4it. And the negative squared would just be gone, which would mean this one would actually stay negative. Do you agree with that? What's going to happen to this one? What's negative cubed?
Or it'll become positive.
That's negative cubed is still negative, but then when I multiply it by this negative, it'll actually become positive. And the I still comes along for the ride. This one will actually stay positive because negative to the 4th is just back to a positive. What happens to this term? Negative to the 5th, a negative number to the 5th. What do you get?
Negative.
You get a negative. And the I is still there. So again, I'm looking at my my non-I terms. I have 1 minus 4t squared over 2 factorial plus 4t to the 4th over 4 factorial, and so on and so forth. I think that next term would be negative based on our pattern, so I think I'll write a minus there instead. And then our I terms, if I took an I out, I would have negative 4t, and then positive 4t cubed over 3 factorial. And then this term would be back to a negative again, 4t to the 5th over 5 factorial, and so on and so forth.
I guess I'd never thought about why I'd always just known those identities, but about what happens when you make the stuff on the inside negative with the sine and cosine. I'd never thought about where it actually comes from. I assumed it was just some trigonometry stuff.
Yeah, which is why I, waste time, I say that in quotes, teaching, because if I don't show you some of this stuff, it can really look like magic and hand waving. But it's like, if we take a little bit of time and just slow down and play around with this, it's like you can build these things and it's not hard. It's just algebra. And you probably have to watch it a second time, but it's kind of like, wow, that actually makes sense. But I want you to,
awesome.
But I want you to stare back at, what we have up here. Is it an exact match?
The second one doesn't match sine. It's the inverse.
Nice. Notice 1 minus junk squared. Hey, that's exactly what cosine is. Do you agree with that? Like, this is the cosine of 4t.
If you pull out a negative, then it would be the same.
Yeah.
For the
But you notice this one doesn't work. It starts with positive x. So it goes positive and then negative and then positive. What did ours do? It started negative and then went positive and then went negative. But all we'd have to do is pull a negative sign out. So then out in front, instead of an I, it'd be a negative I. Do you agree with that? So then we could still say that this was equal to I times the sine of 4t. It's just that we'd have to pull a negative out in front of it. Do you agree with that? So then sort of our second solution. So I'll go back here and call this y1 and this is y2. And maybe I'll kind of throw a box around that. It's like, bam, that was really important. Our second one had a different constant, the same exact e, but it's the cosine of 4t minus I times the sine of 4t.
Well, that's cool because we only switched the sign on the complex part in the like above part. So that does kind of make sense.
Yeah, it does, doesn't it? Because we actually just switched the sign. And so notice that in the end, although we, it really had to kind of let it play out a little bit, it really just threw a negative sign out in front of it. That's all it really did. But notice it's kind of cool that it didn't change cosine. It wasn't like there was a negative in front of that one. Didn't make the whole thing negative. It just made the sign negative. Now,
Had a lot of time on his hands.
so that's kind of cool. And so, you know, in a sense, there's our two solutions. But they're kind of the same solution, right? But then what about this I business? Now here's where it gets really interesting. Let's see, I'm going to show this to you in I'm going to show this to you a little bit more theoretical. So in our case, we got R is equal to 2 plus or minus 4I, right? That's where this all started. Because we just got a complex number for R, but now we're going to all this trouble to write it really different and so forth. But again, we're not happy because there's still a negative, there's still an I in these answers. And so that doesn't really make a lot of sense. Let's do this a little more theoretically. And in accordance with this kind of note sheet that I made for you, notice I, you know, in more general terms, like I called that alpha and that theta. In other words, the theta was the thing in front of the I. So rather than do this with 2s and 4s, let's do this with alpha and theta. So we're saying R equals alpha plus or minus theta I. So if that's true, let's cross the finish line. If that's true, then would you agree that we are now saying that our sort of sweet solution to this is y equals C1 times the cosine of not 4t, but theta t, right? And then C1 was also multiplied by the sine of 4t, except for we had this I that was missing, right? And all I did there is just distribute the C into it. So let's back up a second. That's just this answer, right? It's just this answer right here. That's all I did. I just distributed C1 into it. Wait, except for there was an E out there too, right? Didn't I leave that off? I did. And so I could either multiply that into or, so isn't that what we just said our answer is? Well, at least one of them. And then it went on to say plus again e to the alpha t, except this was the second answer. So it's still cosine of the exact same answer as before, but then this was a minus sign. That's the only difference, right? And a different constant, and there's still an I. This part was, isn't that what we're saying our answer is to this?
Yes.
And so now what I'm going to show you is this troubling I. We're actually going to be able to make that disappear without just erasing it. So let's think about this for just 1 second. Do you notice that, you know, cosine theta t and cosine theta t are all multiplied by, well, a constant, and then they're also multiplied by e to the alpha t. In other words, if I added those together, notice they're added together, don't I just have, well, if I factored everything out, don't I have e to the alpha t in both of them and cosine of theta t in both of them? And then it's just kind of multiplied by like constant 1 plus constant 2. Does that make sense?
Is that
Track
just
with me
a
there?
constant?
But isn't that just a constant? In other words, couldn't I just call that like constant 3? You tracking with that? It's just algebra. And if I do the same thing with kind of the sign values, isn't that kind of exactly the same? Like they have an e to the alpha t. So plus they have e to the alpha t. They also have sine except of 4, or in our case, theta t. But then don't they also have an I? They both have an I. And then don't they have kind of the same thing, C1 plus C2?
Minus.
Minus, thank you. Well, actually, that's a minus sign, right? Because
They
they're
don't become the
subtracted.
same constants. They don't become C3. They
Yeah,
become
that's what was bothering me, because then it would be C3, but this is a totally different constant, right? Like C4. You agree with that? So then couldn't I just say my sort of simpler answer is y equals C3 e to the alpha t cosine of theta t plus, notice it's a plus, C4 e to the alpha t sine of theta t. But remember, there's an I here that we still haven't managed to get rid of.
We're getting there.
We're getting there. But notice I made it smaller. Like back up here, there was sort of like 1, 2, 3, 4 answers, and now there's just kind of like 1, 2. But now I want you to think of something really interesting. Do you remember how you used to write down like what a complex number looked like? What's a complex number?
It's like what you have written up at the top, the real part and a complex part.
Yeah.
API.
So it's got a real part and it's got an imaginary part. So there's actually a difference between complex and imaginary. Complex is both of them put together. Imaginary is just the I number.
I see.
So if I said, it's like number, I don't want to use, let's see what I want to use. Like constants, K
Use
plus,
A. and B.
I don't want to use A and B. I have a reason for that. Just a second. So I'm going to use some different letters. So it's like, I don't know, I'll use K. K1 plus K2, except for this one has an I in front of it. Like that's what a complex number looks like. So K1 and K2 are just constants. Okay. Great. So let's think about this for a second. What if I look at that statement above and I think of that as just a big, giant, complex number up there where, well, all of this is just kind of my K1. And all of this is just kind of my second constant. And then there's the I there that's not part of it, right? So isn't that answer just a big complex numbered answer? I mean, if I told you, what T and theta were in alpha, like, wouldn't that just be a number? And it's behaving like a complex number. That's kind of the idea. So here's where it gets interesting. See if you can follow this. So let's say the original, I'm usually not very proofy in my classes. I usually kind of, skip to but I really want to slow down and try to build this for you. But let's say your original equation. Now remember our original equation, clear back at the start of this, was 1y double prime minus 4y prime plus 20y, right? That was our original equation. This is what the second order differential equations look like. But let's do this a little bit more generally and say that what if your original equation was not 1y double prime minus 4y prime, but what if I just said it's a, b, and c? Like, isn't this what it looked like? Isn't that what our original equations always look like for some a's, b's, and c's? A, B, and C are in the set of constants. Those are just constants. But what I want to do now is actually plug in our answer, like plug that answer in and set it equal to 0. Except for I'm going to use those two terms, kind of K1 and K2.
That would be nice.
So I don't have to write that big ugly mess out, right? So, but unfortunately, in order to do that, I've got to take some derivatives. Well, at least write them, but I don't actually have to take them. But let's just think about these answers. Wouldn't it be this? So if I said A times y double prime, and so here's y, but now I got to get y double prime. Well, wouldn't I have to take if I took K1, wouldn't I have to take its second derivative plus K2 times its second derivative, but then there's an I along for the ride. In other words, I have to do, I'm just not going to write down that I'm going to do it. I'm just going to say I'm going to do it without doing it.
Can you just
then
treat the I like a constant?
Yeah, I'm just going to treat the I just like it's like I'm treating it more like it's an X, like it's a letter. And then wouldn't I have to do the same thing with the first derivative? Take the first derivative of K1 and the first derivative of K2, but then there's an I that comes along for the ride. And then plus C, but then I just put the function in itself without a derivative. So it's K1 plus K2 with an I, no derivative, and that all has to equal 0, right? Now think about the distributive law. If I distribute this into both things and I distribute B into both things, wouldn't I have this? Like, wouldn't I have an A times K1 second derivative and then if I move over to this one, wouldn't I have a B times K1 with a first derivative and finally a C times K1 without a derivative at all? And then plus, if I go back and do the second part of this, wouldn't I have A times K2 second derivative? And there's an I there. I'm not leaving it out, but I'm ignoring it for just a second. And then plus B times K2 first derivative. And then plus C times K2 without a derivative. And all of that is multiplied by I. Is that right? Except for now we have something really fascinating, which is this thing is equal to 0. Why is that really fascinating? Here's why. Your brain's probably hurting right now. I get that. You're probably not feeling like you're tracking this very well. Let's just think about this. Let's think about this complex number. If I had something like K1 plus K2 with an I and it equals 0, how do you get complex numbers to be equal to 0?
Oh, the real
and a little more simply. If you
part.
had A plus BI equals 0, you guys out of here? You guys? How can you get a complex number to be equal to 0?
The real and the imaginary part have to be 0.
Both of them have to be 0. Does that make sense? I mean,
Yes.
if this was a 3 and this was a 0, that's not true, is it? Because 3 is not equal to 0. If this is a 0, fine, but if that's a 5, still not equal to 0. Like, they both have to be equal to 0. Does that make sense? So the only way that is equal to 0, if and only if K1 has to be 0 all by itself and K2 has to be 0 all by itself.
So the K1s represent the cosine terms and their derivatives, and the K2s, the sine.
Yeah. So if you go back up here to K1, if K1 has to be equal to 0, then there's one of your answers right there. If K2 has to be equal to 0, notice K2 does not include I. If K2 has to be 0, then that has to be 0 all by itself. So, and we're done now, we can actually say, I'm looking up above,
The I.
we can actually ignore the I. That's what this comes down to. We can actually say that y would be equal to, I need to go back and get rid of that second derivative because that wasn't actually there. We can actually say that y is equal to just a constant times e to the alpha t times cosine of theta t, and plus another constant e to the alpha t times the sine of theta t. We can say that's the answer without an I in it. The I can disappear. But it's because of this.
Could you scroll down just a little bit? Oh, there you go.
Now, again, the good news is, do you have to do this on a test or something like that? The answer is no. I'm giving you a chance, you that are going on in math, and you're going to need to watch this maybe a second time. And that last part probably didn't feel super good to you. It took me more than once to kind of digest that. But it's entirely based on what I said right here. I was here the whole time, and all we did was algebra until that very last step. And we said, hey, if these two functions added together are equal to 0, and one of these is, K1, and the other one of these is K2, and there's still an I hanging on for the ride. But remember, we're solving a homogeneous equation that's equal to 0. So for the first time, I was able to set this thing equal to 0. Well, if a complex expression is equal to 0, that means each individual term has to be 0 in order for that to be true. Therefore, I can say each term has to be equal to 0. Each term is an answer.
Yeah, I kind of got lost at the end, but I think you cleared it up. So if you scroll all the way up to our original equation and it equals 0, that's where the 0 came from.
Yeah, that's
The
exactly
0
right.
Okay, that
homogeneous.
makes sense. Okay.
In other words, this equation, what we were trying to solve, was equal to 0. So this only works because and that's why a mathematician said, hey, this is really important. It's equal to 0. Let's give it a name. Let's call it homogeneous. I don't know why they picked that name. Notice then what my answer says right here. It says, if you get complex roots of alpha and theta, 2 and 4, notice there's no, there is technically an I in it, but really we're just looking at the 2 and the 4, the alpha and the theta. Notice the answer over here. It says exactly what I just wrote. Constant 1 times, oops, that's not really what I want. Constant 1 times e to whatever that number is times cosine of theta t plus cosine 2, same exact e, same exact theta, but notice there's no I in it.
Can we look at that last, just that last bit that you wrote on the other page? I'd like to stare at it for a second.
Yeah. So from a practical perspective, like this is what you need. You can use this note sheet. You can sort of cheat and use this. You can use what I gave you here, number C or letter C, complex roots. If you get a complex root, here's the answer. You can use that for the test. You don't have to build this stuff. You don't have to understand this, but if, go back and think about it. It's kind of too cool not to understand, but to get your mind around it, to watch me do it once and go, yeah, I get it. You're smarter than me, I will tell you, if you watched me do that once and you can get it. So now
I'm still very
like
confused with the last step, I think, or the last few steps.
So because it's all equal to 0, then the part with all the derivatives has to be equal.
So in a sense, I plugged it back in. I plugged my y back in And of course, to plug y in, you have to take a first and second derivative, right? But what I did is I just wrote down that I'm going to do it without actually doing it. Remember, k was a big, complex, ugly expression with e to the, alpha t and cosine of 4t. It was like a big, ugly expression. So I just said to myself, let's take the second derivative of that. But I'm not going to do it. I'm just going to write down that I'm going to do it.
So at the very bottom, is y equal to 0? Does y represent 0?
No, y is not equal to 0. Y, the entire equation after you take the first and second derivative and plug it in is equal to 0. Y is not
Okay.
0.
Okay.
So
because-
effectively what I did is this is me plugging it in. I took the second derivative here, just like that said to do. I took the first derivative here, just like that said to do, and I didn't take a derivative all, just like this said to do. And then I set it all equal to 0. But then I just noticed, hey, look at that. A is being multiplied by, well, both of these terms added together. So I just said distributive law. So I was able to break it apart into 2 chunks. This chunk here, which had all the K1s in it. And then I just looked at that whole thing and I said, isn't that just like a giant expression? Kind of like let me write this even a little bit differently. Maybe a little bit even more clearly.
So you're just showing that we can disregard the I in this case.
That's
because
exactly
it's
all
equal to
I'm
0.
showing you.
Got it. Okay. I
So
think
if I rename this entire thing just like, I don't know, C5 or whatever, and I rename just this part of it right here, C6, and there's still an I out front, and this is really C5 plus C6, but then that is multiplied by I.
Those really wouldn't be constants, would they? Because they got a lot of variables in them. Those would
That's
be
exactly right. Those aren't constants. That's a good point. I'm writing C like it's a constant, but those aren't really constants. They're like big, ugly expressions, right? But since I am setting this whole thing equal to 0, then doesn't that mean I could separately set C5 equal to 0? Well, that's exactly what I did. I just set that thing equal to 0. That has to be 0 for this to be true. Do you agree with that? In order for this to be equal to 0, doesn't that entire expression up there have to be equal to 0? Correct. That's one of my answers. That's the idea. Doesn't this entire expression up here also have to be equal to 0? Yes. Kind of, in a sense, there's my other answer. So for that reason, I'm able to ignore the I. In order for that to be equal to 0, I kind of can ignore the I.
So those constants at the bottom are going to be different from each other. It's going to be like a C1.
Yes. Yeah, and I'll go back and add that now. C1 and C2, they'll be.
So between the last step and then our final answer, like the step on the last page, all we did was just show that we can ignore the imaginary part because the coefficients have to be equal to 0. So like the real part and the imaginary part have to be equal to 0 since it's homogeneous.
That's exactly right. Irrespective of the I that definitely is part of this answer, in order for it to be equal to 0, then each of those have to be 0 in order for that to work. And that's where my solution comes from. So it's not like a erased I. It's just a recognition that both expressions have to be equal to 0 for the whole thing to be equal to 0.
So could we theoretically have a complex valued solution? Like, is this the general solution?
Yeah. So this is literally a general solution that no longer has a complex answer, which means it actually has an answer now. Like we're actually getting a numerical answer to this. Now let's back off the theory for just a second and do an example. And so, and as an instructor, I've got to be very careful to make these up because remember, what's under the square root sign can be really difficult. So I worked very hard choosing 1, -6, and 34 here. I won't tell you how now, but I worked very hard choosing those numbers. Watch how this comes out. So you say, okay, I know how to solve. And if this is a test, you say, hey, look, second order differential equation, I know how to solve these. I jump without doing any other work to the auxiliary equation, r squared minus 6r plus 34. And I just worry about that. Again, knowing that what I'm thinking here is the solution is e to the rx or rt, whatever my independent variable is. And so then I solve this and I say, okay, quadratic formula, r equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. But then something wonderful happens. Because 36 minus, let's see, what's 4 times 34? That'd be 120 and 16. 136. Hey, 36 minus 136 is negative 100. What's really wonderful about that? What did you get out of that? I worked so hard there.
It's a perfect square.
Perfect square. So if you don't get a perfect square, this is no fun anymore. Do you understand that? Like, you could still do it. It's just that it's really nice if your alpha and your theta are whole numbers. If there's some gigantic, ugly expression, this is no fun. So the fact that this actually continues to 6 plus or minus the square root of 100, and I pop an I outside of that, well, the square root of 100 is 10. And so you have 6 plus or minus 10i. And notice, oh my gosh, not only that, they even both divide by 2. If that had been a 3 down there, does it make sense this is a lot uglier? 6 over 3 is 2, but 10 over 3 is a fraction, so that's no fun.
I'll
But
keep
they
that in
both
mind.
divide
when I-
by 2, so we actually get 3 plus or minus 5i. That's wonderful. That's really nice of me. I will make sure that happens on a test. And so what we do is we say, look, we just identified the answers. This is our alpha. That's our constant portion of our complex number. And the 5 is the one in front of I. Now, why do we care? Because remember, in our answer, vaguely, it's like one of them is with E and one of them is with sine. You understand that? Did I get it right? One of those goes with E and one of those goes with sine. Did I get it right or did I get backwards?
It's backwards.
Backwards. That's why you have a note sheet. The one with the I, that's the one with the trig in it. So the 5 is with the I, so the 5 goes with the trig. So yeah, I got it backwards. And you might have noticed that sheet's really long. Like you're going to use that entire sheet for the next test. Like you kind of need to be relying on this note sheet. So now that I discovered this, I can actually just jump to the answer. Like I found the solution. I mean, this is ridiculous. I'm bypassing all of the, y equals e to the 3 plus 5i. Does that make sense? Like I'm not saying, oh yeah, I know the answer. It's e to the 3 plus 5i t. I'm not writing it that way. Why am I not writing it that way? Because it has an I in it. If it didn't have an I in it, I'd write it that way and I'd be done. You understand that? So all of that amazing algebra and thinking that, again, I don't want to say I did. I actually want to say someone did, because did I invent that? No, I don't think I would have thought of that. So we're saying instead, let's not write it that way, although that's true. Let's write it this way. Y equals a constant times e to the, we got to get this right. It's the 3 that goes with e. And let's see, is this one sine or cosine? I can't remember. Is it sine or cosine?
Cosine.
Notice it actually doesn't really matter, because aren't we going to have both? We're going to have both a sine and a cosine. And we're adding them. No, so according to my note sheet, this is a cosine, but isn't this the exact same answer over there? So it's really just like one with the sine and one with a cosine. So I'll write it the same as the note sheet. So here's where the 5 and the 3 went. And then I rewrite the exact same expression, e to the 3t, except for this time I say sine of 5t. And this is a different constant. I'm done. Like there's the answer right there. I'm finished. That's the answer to this second order differential equation.
So Doug, just for devil's advocate, let's say that was a 3 in the denominator up there, 6 plus or minus 10i over 3.
Mm-hmm.
Would our theta just be 10 over 3?
Yeah, that's not terrible. Instead of 5, we'd have 10 over 3. It's not, it's not
it's
terrible.
doable.
Yeah. And what if it wasn't even 10? What if it had been like the square root of 105 over 7? Well, then 5, instead of 5, you have the square root of 105 over 7. It's not like it's the end of the world.
Just once it gets a little uglier than that, it's probably
Yeah.
way worse.
It's just kind of hard to keep track of. Now, I don't know about you, but you should be a little bit in disbelief. Like, basically what you're saying is we hit a dead end, you drove us through the trees, and we actually just popped out on the road. It's like, that did not happen. Well, yeah, I'm going to show you that it actually did happen. Now, remember what we said in the last section. Individually, this is like answer number 1, and this was like answer number 2. And we just said it was kind of cool that you could just add them together. Does that make sense? But, you know, how do I prove that this is actually true? Well, I just put it back in to this expression up here and see if it's actually equal to 0. Like, let's see if it worked. I'm telling you, we're actually back out on the road now. That was not a dead end. We drove through the forest, popped out on the road, and we're actually getting to where that was a shortcut. Let's just check and see if it actually worked, because you should be a little bit in disbelief. And I'm doing this partially to give you time just to you know, let your brain soak this in. So I'm just going to check. I'm just going to check answer 1. But notice this is going to take some doing, because we're saying here that y equals C1, and I'm just to make it a little simpler, I'm just going to write C e to the 3t cosine of 5t, right?
You don't want to do the product rule like 8 times.
So this is still ugly, but in order to plug it back in, don't I need a first and a second derivative of that? So that means I got to go find y prime too. Is that going to be easy or hard? It's a relative question, but
Just
why do you got to be a
product
little
rule, right?
careful? Yeah, product rule. This isn't going to be super easy because we got the product rule. Now I'm going to assume you're decent at the product rule and probably go a little too fast here. But I'm going to look at the product rule and think of it as junk times junk. So the product rule says the derivative of the first junk, which would be e to the 3t times the derivative of 3t, which is 3, and then times the cosine left alone, yes, plus the ce to the 3t left alone times the derivative of cosine of junk. What's the derivative of cosine of junk?
Negative sign of
Negative sign of junk times the derivative of the junk. The derivative of 5t is 5. Do you agree that's the, do you agree I have that right?
Yeah, it looks right.
Now this was fun. How much fun is it going to be to do yet even one more derivative? Well, I'm very glad to see this plus sign here, but this is like 2 separate product rules now, is it not? So I'm first going to do the derivative of this top statement. Well, the derivative of 3ce to the 3t would be 9ce to the 3t, because I got to multiply by another 3, and the cosine comes along for the ride. Plus the derivative, so the 3ce to the 3t comes along for the ride, but then I got to multiply by the derivative of cosine, which is actually negative sine of the same exact junk, 5t. So that changes the plus to a negative. What else did I forget?
Times the junk inside.
Times the derivative of 5t, which is 5. So 5 times 3 is 15. So this is now 15. So there, that just took care of the first one. Now there's like a plus sign, and I get to do this all over again. So then I think, okay, what's the derivative of 5ce to the 3t? Well, wouldn't it be 5ce to the 3t times 3? So that'd be negative. So I'll just write it as a negative. That'd be negative 15ce to the 3t, and the sine of t comes along for the ride, sine of 5t. But then I say, okay, then the minus 5ce to the 3t comes along for the ride, but now I got to multiply by the derivative of sine of junk, which is cosine of junk, but times the derivative of the junk. So 5, I got to multiply 5 times 5 again, so now it'd be 25. Do you agree now that I have all my ingredients for my recipe? So now I can plug it back into this. So let's just see if that's true. Well, let's actually save a little time rather than try to write that whole thing out. Do you agree? Do you understand the concept of like terms? Let's think just about the, I don't know, sign. Let's think just about the sign for a second. And let's do what this says. So this says y double prime. Okay, what's y double prime that has sign in it? Well, notice it's like terms. It has a C, E. There's 15 of that animal, right? 15 of that animal, that's a sign. But then notice right here, there's another 15 of the same exact animal. Do you agree with that? That's my y double prime. So I have, notice they're both minuses. I have minus 15 and minus 15 of those animals. Do you agree with that? It's 15 of junk. And then I proceed to y prime, and I have to multiply by -6. Well, what do I have here? Well, notice I have, for y prime, I have -5 of those animals. Do you agree with that? But then I have to multiply that by -6, so that's actually plus 30. And then finally, I have to add 34 y's to it. We'll look at y. Notice it doesn't have any signs at all. And sure enough, that actually is equal to 0. Oh my gosh. Let's look at cosine. Let's look at the cosines. Different color. Red. What do I have? Y double prime, same animal, C e to the 3t cosine of 5t. I got 9 of those. And then I have C e to the 3t cosine of 5t, that animal, and then I got 25 of those, minus 25 of those. So that's how many I have so far. Well, what about y prime? Well, again, y prime is multiplied by -6. What do I have? I have 3 of those animals, but I got to multiply by -6, so that's minus 18. And then finally, I need 34 y values. Well, notice what you have here. You have 1 of those, but I got to multiply that by 34. Question, is that equal to 0? Oh my gosh, it is. Like, this answer actually worked. You see what I'm saying? Again, you got to be really good at algebra to, follow that, because I didn't write down the animals. We have 9 of them, 25 of them, 18 of them. I just didn't write what it was. You have a coefficient and a variable. All I wrote was the coefficients.
I guess we could just like write U and V in front of each of those just to
Yeah, exactly right. I mean, I could have named these, and that probably would have been a better thing to do now that you mentioned it. Kind of like your thought. I wish I'd have thought of that myself, man. So if I'd have named this U, then I could have come down here and said 15U and 15U and 30U, that equals 0U. And if I'd have named this V, this cosine V, then I could have said 9V and 25V and 18V and 34V equals 0V. It actually worked as an answer. You see what I'm saying?
Probably want to
Now-
do that after you take your derivatives, though.
Say that again.
Probably want to do that after you take your derivatives, though, so you don't get mixed up with the signs.
Yeah, and I did that.
Right. No, totally. I just mean,
Yeah.
I was like, oh, I wonder if you could do that beforehand, but no.
Yeah, like from the
Nothing.
start. Yeah, if you just call that U from the start, you're exactly right. That'd be a terrible idea, because then you would lose the fact that it's a product rule, and the fact that the 3 and the 5 made contributions to the coefficient and so forth. That's an excellent observation. So, and again, all we did is check answer 1, but because this is a plus sign right here, does it make sense we just be adding a bunch more stuff to it? If we went and redid this for answer 2, we would also get that it worked. And we could even just do them all at the same time if we wanted to, but it's like that already was painful, wasn't it? I mean, I just showed you enough to convince you that unbelievably, like, this is actually working. We actually just got a real answer to something that had an imaginary number in it. Isn't that a trip? And as I said before, you'll see this when we take this back to springs as a model, but it turns out this is the one that actually models real spring motion the best. stuff that vibrates to a stop. It turns out there's a number of different types of vibrations. There's things that vibrate out of control until they break, like the Tacoma Bridge problem. The building that blows in the wind back and forth until it blows bigger and bigger and bigger and then explodes and doesn't work anymore. You know, that's not the typical situation. Typically you hit something, you know, you bounce it, just like I'm doing with this pencil, and it like bounces back to a stop. This is the one that actually models that kind of motion. And so the fact that we just got rid of that imaginary is unbelievably cool, because it's actually the one that models the real world. Okay.
And is this the case because the coefficients for the spring equation usually yield complex roots?
Yeah, that's exactly right. Very well said. Very
So
well
like
said.
that's just kind of what happens normally then.
Yeah. And so
Okay.
remember, those numbers mean things. We'll go back to this later, but like there's a 1 in front of this. If I remember right, that was the mass. And then there was a number in front of this, and this was like the spring the spring
I think that
constant.
one was the damping, right?
One of them was the damping. I can't remember which one was which. This was the speed. This was the one that had to do with speed. So this
Right.
was the, anyway.
Friction.
So yeah, like one was damp, and that's why they give those names. And so yeah, if you give a certain arrangement with positives and negatives, remember what you're after is b squared minus 4ac under the quadratic formula has to come out negative. And if this number is fairly small and this number is positive, then that's going to produce a negative under the square root sign. And so yeah, you're exactly right. If the relationship between the damping coefficient and the spring constant and so forth are just right, the spring is really strong, but it's very damped really hard. And so we're going to be talking about over damped and under damped springs. And yeah, interestingly, those cases are the ones that will produce the vibration that comes to a stop.
And you have
Let me
those
give-
cosines in there too. That's cool because it's
Isn't it unbelievable? Yeah, wait till you see this graph. We're going to graph this right now. We have just time to do one example top to bottom, except for I want you to do it yourself. So, by the way, did anybody look? Do you have that note sheet that I sent? Is that already posted or is it not posted? Anybody happen to look? I'll post that if I didn't already. I
We
think I
have
did.
the final exam note sheet that you're saying we're going to use the whole thing, but we don't
Yeah.
have the math 253 note sheet. I don't know if you care that we don't.
Okay, yeah, I'll post that today. So I'm going to give you this, but then I'm also going to give you some initial conditions so that we can actually find C1 and C2 and go ahead and graph this thing. So I'm going to tell you that at Y0, we have 2. And by the way, notice I'm using the independent variable as being t. And the reason I am is because these model things, and so the independent variable is time. Like, does it make sense? It's more practical if the independent variable is not x, but t, since it's time. So initial time 0, we had 2 pounds of this solution or whatever, or the spring was in position 2. We pulled it 2 away. And at time 0, its speed was 4. So we pulled it away 2 inches and we gave it thump a speed of 4. Now I want to see if you can actually completely solve this differential equation and get C1 and C2. I'm going to give you enough time to get ahead of me. And again, I was very careful to make -12 and 40 here because you're going to notice that beautiful things happen. I just added that Maclaurin series page to my open math under course information if you want to refer to that later. I'm going to do this problem with you. Did you get 6 plus or minus 2i? I hope.
Zoom in.
Maybe that's a good idea. God bless you for that suggestion. Thank you. That's where I watched Dumb and Dumber. Remember that? That's what I did there. That's good enough. So you're staring at this note sheet. It's not, you don't need to make this for yourself. This is what it looks like. You don't need to build this, just use it. So it's kind of important to identify that 6 is the alpha and 2 is the theta. So then you say that my answer is equal to C1e to the 6t cosine of 2t plus C2e to the 6t times the sine of 2t. That's your answer. This is your general solution. While you are continuing, I'm going to go into Desmos and graph that Zambreus.
Does the T have to be X in Desmos for it to graph?
It might. I don't think so. I think I can use T. The worst case scenario, if I go back and change it, not from Y equals, but Y of T equals, then I know it will let me do it.
Oh yeah, that'll work. Okay.
I was going to try it without it and just see what happened. Pretty sure it's going to be okay with this. Why is it giving me A, B, T? It didn't like T, so I do have to go back and say parenthesis T. Did not like t. I wanted it to be a variable.
That's kind of tripping me out a bit.
I'm trying to remember what the initial conditions for this have to be for this graph is kind of out of control. So
If you zoom in, there's some interesting stuff happening right around the origin, I think.
yeah,
Or
I was trying to
more
get this to show up a little bit more obvious.
I think you would have to adjust the frequency.
I think the 2 is the problem. It's the
Right.
it's the 6s and the 2s that are causing the problem here, making this not look realistic. No, that wasn't that useful. So that's not terrible with the note sheet. What we just did there is not hard, is it? I mean, you might, again, unless you go back and look at what I taught you, you might think, I don't really understand what I just did, but whatever, you're saying I got it right. So then now I'm going to go back and find C1 and C2. And so notice if I say y of 0 is 2, then that would be saying that, well, y is 2 when t is 0. Well, e to the 0 is 1. What's the cosine of 0?
1.
Should really do this in the unit circle. Unit circle's here. I'm at that location. Cosine is the x coordinate. That's 1. So I end up C1. What happens with C2 plus C2? E to the 0 is 1. But what is the sine of 0? Sine of 0 is the y coordinate. If I'm at 0 degrees or 0 radians, I'm still right there, but the sine of that is the y coordinate. That's actually 0. And so you just end up with 2 equals C1. So now you know C1, it's 2. What's extremely not good about step 2 of this? Did you discover that?
Do the product rule.
Yeah, you got to take the derivative of this thing. And remember that that's a product rule problem. And so, wow, I got to get y prime. And so you say, okay, y prime is product rule 6c1 e to the 6t times the cosine of 2t left alone. Notice I'm being a little lazy and just writing 2t and not putting in parentheses. And then times the derivative of cosine, which is negative sine, and then also times 2. Cosine is negative sine, so I don't think I blew the product rule for that part of it. So I took care of this. Now I got to keep going and actually do this for C2. Plus, I love plus signs with derivatives. Then it would be 6C2, because the derivative of e to the 6t is e to the 6t times 6 times the sine left alone. But then plus the derivative of sine is cosine, but I also have to multiply by 2. So that would make it 2c2 e to the 6t. And so there's my first derivative. And I am told that that first derivative will be equal to 4 when t is equal to 0. So I'm still in the same exact location. So remember, the cosine of 0 is actually 1. E to the 0 is actually 1. So I actually do get that 6c1 term right there. But anything that has a sine in it, that's going to be 0, isn't it? Sine of 0 is 0. So that term goes away. Sine of 0 is 0. That term goes away. But I will get something here. E to the 0 is 0. Cosine of 0 is 1. I'm sorry, e to the 0 is 1. Cosine of 0 is 1. So I actually get that plus 2c2. Really easy to make a mistake there, right? But I know that C1 is equal to 2. And so then I think, okay, that'd be 4 equals 12 plus 2C2. If I subtract 12 over and divide by 2, I get C2 equals -4. So in the language that I said yesterday, you would say this is y general, or your family of solutions. That's all of them. But now our particular solution, y of p in particular, I just plug those constants in and everything else is just a big old repeat. C2 is -4.
So that's what that P indicates. It's not an indice or something. It's not like one of the solutions. Like a
I'm using the terms general and particular.
okay. They threw it in there in the book and they didn't like say what it was. They were just like, y sub P is this?
Oh, do they use that language in the book? Maybe that's where I got it.
Yeah, they do.
So now we actually have a very particular answer to this solution. And again, it might be worth your time to, go back and literally, well, we're not going to do this, but, literally take the second derivative of the entire expression. I mean, that's a big expression. Take the second derivative of that entire expression, not just one of them, but the whole thing. Take the derivative of that whole thing, take the second derivative of that whole thing, plug that mess back into this and see if it actually is equal to 0. And you'll find that, sure enough, it actually is.
So you don't have to have, can you confirm that it's 0 with the y general answer?
Yes. Yeah.
Okay, just making sure. I thought that's what we did before, but I was just confirming.
Yeah. The general answer will work for sure. But one of the solutions is this. And I want you to think for a second about these initial conditions. And I want you to think about this. This is kind of interesting. These initial conditions. What are these? I hope you've all pushed somebody on a swing. And so you push somebody on a swing. Isn't this what happens? And so here's the ground. And so you're the crazy uncle. So you take them back to here on the swing. Isn't that one of your choices? I'm going to pull them back to there. Which one of those initial conditions is that?
Your initial position, your y.
That's your initial position. You choose to pull them back to there, but is that the only choice you have if you're the uncle? If you're the crazy uncle? What's the second choice you now have if the kid is in this position?
You can choose how fast they go at first.
Yeah, can't you choose to hold them there, but then push them as you let go of them? Then you're giving them an initial speed. Does that make sense? Now, notice the initial speed could be the other direction. Does it make sense? You could actually give them an initial speed that direction, but you could also pull them there and then throw them up backwards, like towards you a little bit more. Do you see why those two initial conditions are not like those are real? Like that's a thing. Like those are the two choices that you have. And do you also agree that this is another example of exactly what we're talking about? Because if you pull that kid back and you could say, I'm going to let y prime 0 equal 0. What are you doing if you decide to do that? You're just releasing them. You're giving them no initial speed. You pulled them back to a certain position. You pulled them 2 meters back. And maybe that'd be -2, depending on which way you made your axis. And then you just let go. So your initial speed could be 0. And then what's going to happen to that kid? Aren't they going to swing and then wobble all the way to a stop? Isn't that what we're setting here? Isn't that what this models? Isn't this what is, again, that's not a spring, but isn't that the concept behind how a spring works? Now, because that problem that I just gave you was contrived, we got values of 6 and 2, right? Now, that was just a practice problem, but when you have a real spring, you don't get 6s and 2s. I have a note here to myself that says, you won't get a spring unless the alpha term is between 0 and -1. In other words, that 6, it's got to be between 0 and -1. For the fun of it, let's go play with that. So if I made that between 0 and -1, so I'll make it -0.2. let's see. Now I'm just kind of playing around with these constants. What do you notice about the right side of that graph?
It's oh, go ahead.
Go
Well, I
ahead.
was saying it's diminishing in size. So it's like the kid's slowing down on the swing.
Yeah. Like this is like you pulled the kid back to here. I guess I can't write on that. You pulled that kid back to 0-2 and gave him a little push. And then do you see them wobbling to a stop? Like that when they come back to you, they don't quite come back quite as far. I'm just looking at the tops of the graphs. And notice, isn't that kind of cool? It's a sine wave. Isn't that a sine wave? And yet what else do you notice? It's not just a sine wave, isn't it? Isn't it damping, if you will? What happens if you just let that kid go long enough? Don't they wobble to a stop? I mean, do you see how powerful this is? And yet, which one was this? This was the one that had the eye in it. So
Do they
if you
ever
choose,
fully reach zero, or is that a limit?
that's a wonderful question. Theoretically, no. Practically, yes. This is again one of those calculus ideas. Is it still wobbling infinitesimally way out here? Yes. Is it practically wobbling out there? No. Because if they're moving a billionth of an inch, you would decide they're still, right?
Yeah, I see.
You're such an engineer, Doug.
Yeah, engineers would say, of course it stops, you idiot. Mathematicians would say, no, it doesn't. And again, that's you deciding which one are you. Are you more practical? Like, dude, it pretty much has stopped at 25. Let's get on with it. I'm an engineer, so I'm saying it stopped at 25. If you're a mathematician, you're like, no, it didn't. And they're both true. Like, they're both cool, aren't they? So you see the sine wave. Where do you see E? Because didn't these have sine waves and E's in them? Where's the E?
Is it the fact that it's decreasing, like kind of exponentially, sort of? Oh, you can kind of see it. Like it's kind of the peaks kind of have like a downward curve.
Yeah,
Like an exponential.
you're on it. I'll show you this more later when we get to practical stuff because we're kind of out of time here, but you obviously see the sine wave. But what do you notice if you look at those peaks? I think this is what Daniel was saying. Like that's the y equals e to the negative 0.2t right there that was in the problem. And if I graph that along with it, that's exactly what you would see if I remember right. I'm not sure if I remember right. Let's go back and do it. Y equals, the only thing I don't know is what coefficient do I have to put in front of the e to the negative 0.2t. I'm not sure that, I think I might have to get that coefficient correct in order for this to look really good, but this will at least give you the basic idea. I'm going to put an X here so I don't have to type it. And let's see, do I have to, can I just put A in front of it? Is it exactly the same? I don't remember. I guess it isn't exactly the same. I'll put a different coefficient in front of it. Isn't that amazing? Look at that. Boom, it's perfect. If you get the right coefficient in front of it, and by the way, the reason for that, the reason it's not 2.2 or 1.8 has to do with the fact that that's not just a sine wave, it's a sine wave plus a cosine wave. But notice it's damping. Like this is an example of a damped spring, or like where gravity is working on the kid on the swing. And so they're actually slowing down according to E. And again, one of the things I love to say in my classes is my main goal in this class is to ruin your life. I want you next time we go to a park to be, everybody else is just swinging and having fun, and you're staring at that kid going, he's slowing down according to an E, an exponential function, and you could actually measure it and model it. And that's kind of what I want to do with one of our projects. And actually, I never thought about the swing example before. It's kind of making me think it'd be fun to do that, like literally with a swing.
Field trip to the park.
My brain is working now. I'm thinking we should actually meet. We should meet and go to a park. We should actually try this. We should push all the little kids off the swing. Get out of here, kids. We're doing calculus. And take measurements and see if we could model like how that actually works. See if we could find that equation. Again, do you see that's the point? and I'll shut up after this, but it's like no one's going to hand you the nerdy equation I just gave you and say y double prime minus 12y prime plus 40y equals 0 and say, can you solve this? It's more just going to be, hey, that building is wobbling back and forth, you know, like, can we model how that's working to make sure we build it strong enough so that doesn't break it? And so you're going to have to write the equation yourself. And so that's what the project is could you somehow find something that oscillates to a stop? And then could you go find the equation that actually models that? So I'm thinking that'd be awesome if we met at the park, everybody brought some lunch, we tested this out, pushed all the kids off the swing, went over there and took measurements. You should be blown away. This is pretty amazing stuff. All right, let's get out of here. As usual, I'm not going anywhere right now, so stay after if you want. Otherwise, what are we doing tomorrow? We are looking at what if it's not equal to 0? What if our equation is not equal to 0, but what if it's like equal to t or something like that? Could we still solve it? But fortunately, for the spring example, what we just did models most of it. But remember, I said that the external forces are gravity, and don't we always have gravity on a swing? And so we're actually going to need this not to be equal to 0, but to be equal to something else. And so we're going to have to think about that a little bit. So that's tomorrow's lovely discussion.
Thank you, Doug.
Thanks, Doug.
Thank you all.